Hi, in this video we're going to be looking at two more examples of applications of exponential functions. So this kind of question where we're in context here and we're going to use what we know about exponential functions and be able to solve some equations using them, that sort of thing. So let's look at two more here. In this one here, we've got the population of a particularly endangered species and it's declining exponentially. So as soon as you read that, declining exponentially, straight away I'm thinking that there's going to be some kind of model where you've got the population is something times, I shouldn't use an a there, let's say something k times a to the power of t, something like that. That's what I'm thinking, because we know for exponential functions we've got the variable in the power up here rather than in the base, so a is some number. Now we also should know from the last video of that a little bit about this number here. If we're increasing, a is going to be greater than 1. So when we're adding 10%, a is 1.1. When we're decreasing, like this situation, what you're going to find is that a is between 0 and 1. Okay? So when things are going up, increasing, a greater than 1. When things are going down, like the value of our car was decreasing by a certain percentage, then you'll find a is between 0 and 1. So that's some helpful little things. As soon as you see that declining exponentially, it's going to be something that looks kind of like this form up here. So let's answer this question here. We've got the populations from 2000, 2005, 2010, 2013, and we've measured those. By what percentage is the population declining each year? Now in the last video I was able to work out that percentage by comparing from year to year, but notice in this case that we've got actually a 5-year gap. So this is a little bit trickier to think about. So let's do this. So remember, if we were just going from year to year, what I did is I just compared the ratio of the two. So let's say if we had 5,760 was the first year, and the next year was 5,700, and the next year was 5,620, etc., etc. If we went from year to year to year, what I did is I just divided the second term by the first term, got an answer for that. Then I divided the third term by the second term, and hopefully those two should be approximately the same thing. From the last video we had, it was around about 2% or 1.02 each time, which showed we're going up by 2%. We'd expect the same thing here, that you're multiplying by the same thing each time to get next year's number. Now in this case we've gone 5 years. We've gone from 2000 to 2005. So let's think about how we do this. Here's 2000, 2001, 2002, 2003, 2004, 2005. Alright, cool. So I reckon that we're starting with 5,760 here. We're timesing it by a certain number. I'll call it A for now, to get this one here. Then we're timesing this number here by A again to get that one there. Then we're timesing it by A again to get that, and A again to get that, and A again to get the number in 2005. In fact, I've taken 5,760 and timesed it by A 5 times to get me the value from 2005. I hope that made sense. So we're not just going year to year, we're not just timesing it by 1, we have to actually think here we've timesed it by that number 5 times to get to our number in 2005. Again, assuming that the growth is declining exponentially. So that gives me a to the 5 is 4460 divided by 5,760. Now on our calculators, this is definitely in the calculator section, we'd have to work out the 5th root of this thing here. Okay, put that in on your calculator and you get around about 0.95. Okay, so in other words, if you remember the percentage scale that I showed you before, here we are at 100%, which is 1. If we're here at 0.95, that represents a 5% decrease. Okay, 5% off 100% is 95%, whereas the decimal is 0.95. So just looking at 2000 to 2005, I'm thinking that there's been a 5% decrease in the population every year. Now let's just check and see if that 5% figure is correct. So what I'm going to do is compare 2005 to 2010. Again, we've got a 5-year jump. So you can see the 2010 figure is 3,450. So I could write a similar statement to what I've written here. 4460 times a to the power of 5 is equal to 3,450. Okay, so I'm going to solve that. 3,450 divided by 4460. I'm going to do the fifth root of both sides, and that will just leave me with a is, again, I'll do that on my calculator, and you can check that again you get approximately 0.95. So it's looking good that the population is decreasing by 5% each year. Now if that value of a turned out to be 0.8, that would tell me that the population was decreasing by 20% each year. Okay, I hope that makes sense. So we're going down 20% each year if we get an A value of 0.8. In this case, we can say the population is going down by 5% each year. So let's come up with a model now. The population, in this case, of this endangered species of animal is your initial population. We always write that at the start. So the initial population was 5,760 times 0.95. Now, I don't want to just do that to the power of t, because for the values of t here, we're actually using the year numbers. So if we define t to be number of years from 2000, that would be our model there. But in this case, we're talking about including the actual year number in that. So we'd have to say something like t minus 2000, and that would be our correct model. So then when I put in 2005 into that formula, you could see that's putting t equals 2005 would be, I'd have power of 5 there, which means I multiplied 5 times by that, which is exactly what we worked out before. Okay, so predict the population for this animal in the year 2025. We now just need to say, well, 2025, and just put it into our formula that we've just worked out. 2025 minus 2000. And we get our calculator out, and it's approximately 1600. Okay, so by the year 2025, the population will be a roughly 1,600, and that's of course assuming that this rate of decline, 5% each year, continues. Last example that we're going to look at, we've got the graph in this case here, which is a little bit different. We're actually given the formula that I kind of outlined before, and told us a, because a is greater than 1, which means it's going up. Let's go through these questions here. So the graph on the right shows an exponential growth situation, and we've got the rule, determine the value of a when t is equal to 5. This is kind of reading off the graph, this one. So we've got t equals 5. I can see that's spot on 400. So for part A, what's the value of a when t is equal to 5? It looks like a is equal to 400. For part B, the value of a when t is equal to 8. Okay, so I'm going to go to 8 here on my graph. I'm going to go straight up to the graph from 8 and go across, and it's right there. This would be much better if I had a ruler. So looking at that scale there, it looks like about 875. In fact, it's spot on 875. So I can say a is equal to 875. Now you might notice in our last ones, our exponential graph, we had like a starting value like this, so we could identify this initial starting value. So when I came up with the formula, I could have said something like that's 150 times a to the power of t. Okay, that value at the start is always that point right there. In this one here, however, it does not stretch back that far. We cannot see where it's going to go through the y-axis, so we need to do a little bit more work here. Hence, now I've got 2 points, I'm going to be able to do that. So part C asked me to find the constants a and k. So let's do that. So we know that we've gone from t equals 5 across to t equals 8, and remembering this is an exponential situation, so each time we're timesing by a to get the next number, okay? Times by a and then times by a again. So we said the value at 5 is 400, the value at 8 is 875. What have we done to go from 5 to 8? We've multiplied by a 3 times. So we've gone 400 times by a, that will give us the value at t equals 6. Then times by a again will give us the value at t equals 7, times by a again, the value of t equals 8. So we've times by a 3 times, and that gives us 875. So we can say a cubed is 875 over 400. Again, to undo a cubed, I'm going to do the cube root of both sides. So that gives me that a is, and you get your calculator out, about 1.298. You check that on your calculator that you got that correct. So I know now that the relationship is of the form a is equal to k times 1.298 to the power of t. Now that also tells us that the growth rate here is about 29.8%. We've added on 29.8% to get to 1.298, so we're growing by quite a bit here. So how can we find the value of k at the start there? Well, now we've got this equation here. We've got a few points on this curve, so I can just substitute one of them in. For example, we found that when t was equal to 5, that a was equal to 400. And I could use the other point as well. I could use t equals 8, a equals 875, but I'm going to do that one. So again, we get our calculator out. We do 1.298 to the power of 5, and I would be using the exact value I got from the previous question there, work out what that is, and then divide both sides by that. So 1.298 to the power of 5 is going to be my value of k. So k in this case here is around about 109. So therefore we've got our equation. A is equal to 109 times 1.298 to the power of t. So there's our variables. T is along the x-axis, a is along the y-axis. So now we can answer the other questions. So D says, what's the value of a when t is equal to 0? When t is equal to 0, we've got 109 times 1.298 to the power of 0. We know this is equal to 1. Anything to the power of 0 is 1, so we've got 109. So that's our initial value. So if I was to take this graph back and zoom it along here, it would go through there at 109. Okay, and the last question, nearly there, says the value of t, correct to one decimal place, for which a is equal to 4,000, assuming the growth rate suggested by the graph continues. So we want to know when we're going to get to 4,000. So you can see our graph only goes up to 1,000. So we're solving this equation. 4,000 equals 109 times 1.298 to the power of t. Okay, let's solve this thing. First thing I'm going to do is divide both sides by that. I want to get this on its own first. I think that makes it a little bit nicer to look at and understand, but essentially we're going to use our calculator anyway, but that would be my first step here. 4,000 divided by 109 equals 1.298 to the power of t. Make sure you haven't rounded, so like this value here you should have on your calculator. This value here, the 1.298 value, you should have on your calculator. So I'd be wanting to use the exact values in there when I'm doing this step here, the exact calculation. So this gives you 4,000 divided by 109 is about 36.7. So now it's time to get out our calculator and use the solve function. Okay. You could actually get your CAS out and draw 1.298 to the power of t and draw y equals 36.7. Use the trace function to find when they intersect. But it's pretty easy just to use the solve function and make sure you go comma t, and you get 13.8 for the value of t here. So in this context here, it's this one here doesn't tell you t's time or seconds or months or whatever. So if this was like minutes or whatever, you'd want to write your answer as 13.8 minutes. So it's just a little bit over here that the graph is actually way up there at 4,000. Okay, I hope that gives you an idea of how to do those problems.